Good morning and welcome to Collaborative Statistics. Today we are on Chapter 13, which is the F distribution and the ANOVA tables, one way. You can do larger ones, but we're just going to look at the one-way ANOVA table for this book here. And an ANOVA table allows you to, remember in Chapter 11 we did two hypotheses. We had two means or two populations and we were comparing them. This allows us to test, are there more than two averages that are the same? Okay, so we want to test multiple groups and see, is everything the same for them? And to do this, we have to do an analysis of variance, which they abbreviate down to ANOVA. And the F distribution is the ratio that is calculated to test an ANOVA table. So that's where these two pieces come from. So in a one-way ANOVA, we are trying to see, is there a difference between several groups? And the statistic, as I said, is the F ratio, or the F distribution. And there's 5 assumptions: that they're all normal, the samples are random and independent, the populations have equal variances, the factor is categorical, and the responses are numerical. So we have to have, if we have yeses and nos, we have to turn those into numbers because we need to be able to average stuff. And so we will, we can only have numbers pieces for these stuff for this to work, because obviously we're doing means and standard deviations. So we have to be able to add these together and get a normal, useful total. And so we're going to be testing, is mean 1 equal to mean 2, mean 3 equal to mean 4, all the way up until how many. So we can do this for 3 or 300. And what we're going to have is our null hypothesis is that they're all equal, and the alternative is that at least one of them is different from another one. So if that fails, then they are not all equal, and therefore we have the alternative. So to calculate the F ratio, we have to calculate it's a fraction. And we have, the numerator is the variance of between the samples. So it's the variance in the sample means. And the bottom one is the variance within the samples, or the averages of the standard deviations, the variances. And we're going to have two things that we're going to come into degrees of freedom in this. K, which is how many groups we're looking at, how many means are we comparing. And N, which is the number of samples, just like it was before. What is the total number of things that were counted? So the sample sizes of the groups don't have to be the same in this to calculate this, but so that's why we have N and K, and we will subtract them, and you'll see that in a second. So we have all these formulas, the SS, the sum of the squares of the total. We have the sum of the squares between, this is our numerator. The sum of the squares within is our denominator, so we just take the total and subtract off the between. Then we find our mean squares, which is the sum of the squares between divided by the degrees of freedom. And in this case, degrees of freedom is K minus 1, so the number of groups minus 1. The mean squares of within is, we take the sum of the squares within, divided by the degrees of freedom, which is the total number of things minus the total number of groups. So that's where that K comes from. And then we have our F value, which is a ratio between the mean squares between over the mean squares within. So it's a long process, but again, we're going to be using a calculator or a computer to do this. We're not going to do this by hand. So don't have to worry about calculating all those little things. And if the groups are the same size, there's a simpler way to do it. We take the standard deviation of the means, multiplied by n, and divide that by the standard deviation pool, this variance pooled, which is just the average of the standard deviations that we have, the average of the variances that we've been given, and that gives us our F value. This is what an ANOVA table looks like. So if you do this in Excel or Minitab or R or any statistical package, it's going to come up with this table basically. You're going to have your sources. They're going to have some that may or may not have a title, but you'll have your between, your within, and your total. You have your sum of squares, your degrees of freedom, your mean squares, and your F ratios. So here you'll calculate the sum of squares between, sum of squares within, sum of squares total, degrees of freedom, which is k minus 1, the number of groups minus 1. The degrees of freedom of you're within is the number of things, total number, so we count those up, minus how many groups there were. And the total still has the n minus 1 degrees of freedom, because we add these up, the k's cancel out, we get n minus 1. The mean squares, remember, is the sum of squares between divided by degrees of freedom. Sum of squares within divided by the degrees of freedom, because it's our mean squares within. And our ratio here is our mean squares between divided by our mean squares within, and it will usually give you the p-value. So we're again going to compare the p-value to alpha to determine whether or not we reject or not reject. The other thing we can do within an ANOVA table and the F statistic, well actually not an ANOVA table, but the F statistic, is to compare whether two variances are equal to each other. Okay, so we need to be able to know that the populations are normally distributed, which we were always assuming, and that they are independent of each other. Then what we do is we have our null hypothesis, which is that sigma 1 is equal to sigma 2. And we find our f value, which is f is equal to the variance of the first one divided by the variance of the second one. And then it will give us an f ratio, which we can then calculate our p-value from, and then from there compare that to alpha. All right. The f statistic is not symmetric, so that's one thing to notice about it. When you look in your book, you'll see a graph of it, and they change again depending on sizes, but it is not a symmetrical tool, so something to compare. And so this is everything. I will see you on Saturday. Have a good day.